All right, ladies and gentlemen, welcome back for another round. It feels like it's been forever since I've been able to talk to you guys here. So let's go ahead and get right after it today. We're going to take a look at bond energy this afternoon, and we will look at energy and define energy as the ability to do work and or produce heat. Now, I have to be completely honest with you. This is where we're going to be focusing most in this particular unit of thermochemistry and thermodynamics, i.e. thermal energy, all right, that heat production. And so what I've got drawn on here, and you might want to go ahead and pause, is I've got a potential energy diagram for the formation of H2, and you'll notice, like, I've got it divided into 4 different sections. So when you pause this video, there's a couple of things that you need to pay attention to the details. Number one, notice the 0 on the axis is actually way up there. All right, and then my axes labels are potential energy and distance. Go ahead and get the name of it, all right, and then cut it into 4 different sections. And then the curve of this green turquoise line, that's actually important. It needs to kind of be very similar to that. Okay, and so now that you've got that drawn, we're going to go through the whole idea of what happens in as far as energy is concerned in the formation of that bond between 2 hydrogen atoms. So our very first scenario that we're going to look at is I've got 2 hydrogen atoms and they're really far apart. All right, and so notice the further they get apart, I'm looking at my distance on this x-axis. The further they get apart, the more likely my energy is going to be closer to 0. And so distance does matter here, right? And then my second situation, what now I've got is I've got my hydrogen atoms in proximity. They are feeling some attraction, right? Those nuclei from each of those hydrogen atoms is becoming attracted to the other electron of the other hydrogen atom. Now, the attraction-repulsion that we're going to be talking about in here today is actually based on Columbic forces. Now, remember Columbic forces, the force of attraction is proportional to charge 1 times charge 2 over r squared. So really, it's a charge over distance argument here. And remember, opposites attract, likes repel, right? Another way that you may hear me refer to this, so you may want to describe it, is they are known as electrostatic attractions and repulsions, right? And that's the attraction and repulsion based on positive, negative charge interactions, all right? And so that second scenario, they've become proximity, and now they're feeling some force of attraction, and notice what happens to the energy, to the overall potential energy between those 2 atoms. It's actually lowering. All right, and so by increasing the force of attraction there, by becoming closer to each other, they're actually lowering and entering a lower energy state. All right, and then here they actually, this third scenario, let me go back to my red. So this is my third scenario, and now what we see is they actually have overlapped, right? They have reached this perfect low energy state here. Right, and that needs to be notated on here. This is a low energy state, and this is actually where the bond is formed. This is where my attraction between the nuclei and the other atoms' electrons is the greatest, and the repulsions that we're getting from the 2 nuclei being close to each other is also, I guess, at its lowest state, if you will. I guess the overall way to think about this is the overall attraction is definitely outweighing the overall repulsion that the atoms are feeling at this point. And what we would say is that we would term this as the H2, the hydrogen bond length. And so when hydrogen forms that bond of H to H, this is the bond length that we'll get to, and it's driven by those Columbic or those electrostatic interactions and that distance between them and the fact that it represents a low energy state. To get any further or any closer, we have to actually put in energy to do it. All right? And then my fourth scenario over here that we want to make sure that we're really, right, is the fact that when my nuclei get too close and now there's an overall repulsion and they're putting they're wanting to push away. Now notice when I have my repulsion here, I've started to increase my amount of energy there. I had to put in energy to push them closer together, and so what they'll do is rather than actually putting in energy to push them closer together, they'll come back and they'll head, everything kind of fills in towards that low energy state. Now, a couple of takeaways from this. Number one, Energy is released when bonds are formed. Notice I go from a zero energy state to a low energy state as my bond is formed. All right? And my bond formation is driven by these electrostatic or these Columbic interactions to reduce repulsion and maximize attraction. All right? And then another thing, I'm gonna man, let's talk about this. If I'm going back that direction, if I'm going to break this bond, you need to understand I have to put in energy to break those bonds. All right? So big takeaways here, ladies and gentlemen. Energy is released when bonds are formed, right? That bond formation represents a low energy state, and then we must put in energy to actually break bonds. Okay, and so now what we've done is we've just moved on here, and we need to understand, now that we talked about the energy associated with bond formation and breaking the bonds, we need to understand and just kind of realize all chemical reactions involve two things. We're going to break existing bonds, and then we're going to form new bonds. And so you have to understand this is going to be an energy input, and this is going to be a release of energy. And so our overall, you kind of realize where I'm taking you, our overall net energy, how much energy is going to go in or come out, is really based on how much energy did we have to put in to break the bonds versus how much energy we're going to get out when the new bonds are actually formed. And so it's because of this that all of our chemical reactions is going to or are going to involve some kind of energy exchange, and we're really, just like I circled it, we're going to be looking at the thermal energy part of that in these reactions primarily during this unit. All right? And again, understanding heat is either absorbed or heat is actually released, and hopefully you're starting to think of some terms here called endothermic versus exothermic, right? We're actually going to learn exactly what those are in this particular unit. And then I guess it would make sense to go ahead and draw these energy diagrams. I'm going to start drawing them, but we understand that an exothermic energy diagram, I've got reactants and products. So my potential energy here is actually decreased, all right, versus, and this is my exo, versus my endothermic reactions where I have a net energy increase. This is my reactants. These are my products. Now I'm going to go ahead and pause this real quick, and I'm going to fill in some other stuff on here. Okay, and so what I've done is I've just labeled everything. I've got the delta H's, and hopefully you remember that from pre-AP chemistry, but delta H is essentially, or not essentially, it is, this is my enthalpy change, and that's the terminology that we're going to use to describe this heat exchange between the system and the surroundings here. Now, one thing I definitely do want to I guess impart upon you right here is that this is known as, enthalpy is known as a state function. And so really all I'm focused with is where am I beginning and where am I ending? That's my difference between my enthalpy here. It doesn't matter how I get there, it's just where do I start versus where I begin. All right? And this will become important later on here in just a couple of seconds, because I'm going to show you that, hey, we can reverse some of these enthalpy values just by, or I guess change the sign by reversing the reactions. And so you really need to understand we can do that because it doesn't matter whether I'm going from reactants to products or from products to reactants. The difference between those 2 points is the same. It's just whether one is positive versus whether one is negative. And let's go ahead and do that. You should understand that this is a negative value for an exothermic energy diagram, right? Energy was released into the environment. And then for my endothermic energy diagram, it should make sense with you looking at that right there, that is a positive enthalpy change, all right? And please understand the idea that this is a state function, just difference between beginning and ending, all right? Okay, and so now what we're going to do is we're actually going to define something. We're going to define bond energy, all right? And so energy is the amount of energy needed to break a bond. It should make sense to you that these are always going to be positive values because they're always going to require an input of energy, right? I refer you back to the graph that we started with, right? to separate those atoms from each other, we actually have to put in energy to overcome those Columbic attractions, those right, between atom forces, like inside, that's my bond. I've got to break those bonds. All right, and so there'll always be positive values, and my bond energies are going to be table values, right? We know what they are. We can give them to you under certain conditions, and so if I'm looking at a reaction where I've got reactants becoming products, it should make sense to you that the overall net, right, how much energy is released or absorbed here, would be the sum of my bond energies of my reaction or my reactants, and then also a function of the sum of my bond energy for my products. Now, these bond energies of my reactants, those are always going to be positive delta H's. They're always going to be positive. I have to put in energy to break those bonds. The value of my product should always be a negative value. And so with these, we must flip those and change the sign from a positive to a negative. And that should make sense to you now because it is just a state function. Whether I'm going forward or reverse and breaking that bond, it's the same amount or same place from going point A to point B. It's just a difference, right? That is a state function, all right? And so to come up with this overall enthalpy of a reaction, right, with the subscript reaction means the overall, the net, how much energy is released or absorbed by the reaction as a whole, you should know that you just have to sum up all of your bond energies. Now this takes into account, ladies and gentlemen, that you have flipped the sign of the products. It does take that into account. You have to remember to do that or you're going to end up with the wrong thing, all right? And then based on that, remember if it's a positive delta H, then I would be looking at an endothermic reaction. If it's a negative delta H, I would be looking at an exothermic reaction. All right? Okay, so that was a lot, ladies and gentlemen. Hopefully you got your questions down. If you had any, I'll see you in tutorials to get those answered. Otherwise, I will see you in class.